Welcome to the deep dive. Today, we're tackling something really fundamental, maybe one of the trickiest parts of modern physics, quantum non-locality.
It definitely pushes our everyday intuition way past its limits.
Yeah, and our exploration today is really sparked by John Stewart Bell's work, his theorem, and actually a recent conference the Essentia Foundation held looking back at its impact.
Always good to remember what Feynman said, right? Nobody understands quantum mechanics. Even physicists find it, well, deeply weird.
Absolutely. And that's kind of our mission here for you in this deep dive, to unpack this seemingly paradoxical idea of non-locality, using insights from our sources, trying to make it clearer and showing why it's actually so important.
And we have some great guides. Our sources feature Professor Sandhu Popescu from Bristol University. He's won the John Stewart Bell Prize, among other things, and Dr. Lydia Del Rio, a research fellow at Essentia, who's deep into quantum information.
So real experts who've thought about this stuff a lot.
Definitely. And interestingly, the source material kicks off with this sort of analogy about trade-offs, like the old saying, good, fast, cheap, pick two.
Right. Implying nature itself might have these built-in constraints, these fundamental trade-offs that aren't immediately obvious.
Exactly. It kind of sets the stage for why quantum mechanics often feels so counterintuitive right from the get-go.
Okay, so maybe a good place to start to see that weirdness in action is the classic double-slit experiment.
Perfect example. Yeah, the basic setup is simple enough. You have a source shooting out electrons, one at a time. Then there's a screen with just two narrow slits in it.
And behind that, a detector screen to see where they land.
Right, and what happens is, well, it's baffling. Each electron hits the detector screen at a single point. Click. Like a tiny particle.
Okay, that seems normal enough. Particle behavior.
But when you let lots of these electrons go through, one after another, and build up a pattern over time, you don't just get two bright lines behind the slits.
No. What do you get?
You get an interference pattern, alternating bright and dark bands, just like you'd expect if waves were passing through both slits and interfering with each other.
Wait, even though the electrons are going through one by one, how can a single electron interfere with itself?
That's the million-dollar question. It behaves like a particle when detected, but somehow like a wave when it's passing through the slits, exploring both paths simultaneously in a way.
So for any single electron, you can't actually predict exactly where it's going to land. It seems random.
Utterly random for one electron. But collect enough data points, and this incredibly precise deterministic probability pattern, the interference pattern, emerges.
It's like, you mentioned the biased coin analogy. One flip is random, but over many flips, you see the bias clearly. Is it like that?
It's similar in that there's individual randomness, but collective predictability. But crucially, in quantum mechanics, this randomness isn't thought to be because we're missing some information, some hidden variables controlling the coin flip, it seems. Fundamental, baked into reality.
And this fundamental randomness, this is what Einstein really struggled with, wasn't it? The whole God does not play dice idea.
Exactly. He deeply believed reality should be deterministic at its core. But, as Professor Popescu points out in the source, maybe a non-deterministic theory isn't a flaw. Maybe it actually allows for, well, a richer, more flexible universe, more possibilities.
That discomfort, though, led Einstein, along with Podolsky and Rosen EPR, to formulate a really powerful argument, didn't it, back in the 30s?
It did. Initially, Einstein had tried finding outright contradictions in quantum mechanics. But after debates, especially with Niels Bohr, he sort of shifted tactics. He started arguing not that quantum mechanics was wrong, but that it must be incomplete.
Incomplete, meaning there's more to the story.
Yeah, that there must be some hidden factors, these hidden variables we mentioned, that quantum theory wasn't accounting for. If we knew these variables, the apparent randomness would disappear and everything would be deterministic again.
Okay, so how did the EPR paper try to show this incompleteness?
They proposed a thought experiment. A simplified version goes like this. Imagine a source that emits two particles, let's say flying off in opposite directions towards distant detectors. And each detector can measure some property of the particle, maybe its spin, but let's just imagine it makes a light flash either red or green.
Two possible outcomes at each end. Got it.
Now, what's observed experimentally when you prepare these particles in a special entangled state is a perfect correlation. If the left detector flashes red, the right one always flashes red. If the left flashes green, the right always flashes green. They always match.
Always, no matter how far apart they are.
Always. Instantly, as far as we can tell, they seem linked. This is entanglement. Measuring one particle seems to instantaneously influence the possible outcome for the other, regardless of distance.
Right, and this is where Einstein's spooky action at a distance comes in. That phrase wasn't in the original paper, but captures the idea.
It captures his unease, definitely. His argument was, how could measuring particle A possibly affect particle B instantaneously across a vast distance? That would seem to violate the cosmic speed limit, the speed of light.
So to avoid that spooky, faster-than-light influence,
Einstein reasoned the particles must have already decided or carried the information about their outcomes right from the moment they were created at the source. Like they had hidden instruction sets. These would be the local hidden variables. Local meaning the instruction set is with the particle. No distant influence needed.
so the correlation isn't spooky action, it's just revealing pre-agreed properties, like finding out two separated twins both have blue eyes, they were born that way.
That was precisely the argument. Local hidden variables would explain the correlations without faster-than-light communication, making quantum mechanics incomplete because it didn't describe these variables.
And that idea seemed plausible, right? It preserves locality, gets rid of the spookiness.
It did seem plausible, and for about 30 years it remained mostly a philosophical debate, until John Bell came along in 1964.
Bell's theorem. This is the crucial turning point.
Absolutely pivotal. Bell figured out a way to actually test this idea of local hidden variables experimentally. He derived a mathematical inequality.
An inequality, like
Yeah.
a mathematical rule.
Exactly, a rule that any theory based on local hidden variables must obey. It sets a limit on how strong the correlations between the measurements on the two separated particles could possibly be if those correlations are just due to pre-agreed strategies or hidden instructions.
It's interesting, though, that it took 30 years after EPR, and even then, Bell's paper didn't exactly set the world on fire immediately.
Yeah.
Why the delay and the initial quiet reception?
Well, as our sources suggest, physicists were incredibly busy using quantum mechanics. It was unbelievably successful at explaining atoms, molecules, solids, radiation, practical stuff.
The shut up and calculate phase.
Pretty much. There was so much progress being made applying the theory that digging into these really deep foundational questions about reality, especially involving particles miles apart that weren't obviously interacting, it maybe didn't seem like the most pressing issue for many working physicists.
It felt a bit philosophical, like debating the mechanism of a drug that clearly works wonders.
Sort of, yeah. And the original EPR paper itself and Bohr's reply were quite dense and complex. It maybe wasn't immediately obvious just how deep the challenge was. It took time and maybe Bell's clear mathematical formulation to really grasp the metal.
So Bell comes up with this inequality. How does it work, in principle? The source used a game analogy.
Yeah, the game analogy is helpful, though simplified. Imagine two people, Alice and Bob, far apart. They can't communicate. On each round, they each randomly get asked either question 1 or question 2.
Random questions.
Based on the question they get, they have to answer either red or green. Now, there are rules for winning. For example, if they both get question 1, they win if they give the same answer. If one gets 1 and the other gets 2, they win if they give the same answer. But if they both get question 2, they win only if they give different answers.
Okay, specific rules based on the questions.
Now, the crucial point, if Alice and Bob can only rely on strategies they agreed on beforehand, which is the analogy for local hidden variables, preset instructions, Bell showed mathematically they can't win this game more than 75% of the time, averaged over many rounds. There's a statistical limit.
75%, that's the Bell inequality limit for local hidden variables in this game.
That's the limit. But if Alice and Bob share a pair of entangled quantum particles and they perform measurements on their particle based on the question they receive, like measuring spin along different axes, quantum mechanics predicts they can win more often.
How much more often?
Around 85% or even slightly higher, depending on the exact setup. Significantly higher than the 75% classical limit.
And the experiments, what did they find?
The experiments, starting with Clauser, Aspect, Zeilinger, and others, work that earned a Nobel Prize, by the way, have overwhelmingly confirmed the quantum predictions. They consistently violate Bell's inequality. They achieve the higher win rates predicted by quantum mechanics.
Wow. So the experiments basically say, local hidden variables can't explain reality. The Einstein-Podolsky-Rosen hope for a classical underpinning doesn't work.
That's the staggering conclusion. Nature is weirder than Einstein hoped. The correlations are stronger than any local predetermined explanation can allow. This forces us to confront non-locality.
This idea that the entangled particles are connected in some way that defies classical separation, even though, as you said, we can't use it to send messages faster than light.
Correct. It's a correlation, not communication. Measuring one particle instantly tells you something definitive about the other, no matter the distance, but you can't control which outcome you get, so you can't use it to transmit information controllably. It preserves causality in that sense.
So this leads to the no-go theorem concept mentioned in the source, like the good, fast, cheap trade-off again.
Exactly. A no-go theorem basically says, here's a list of nice, reasonable-sounding assumptions about the world. Unfortunately, you can't have them all simultaneously. The experimental facts forbid it.
And in the context of Bell's theorem, what are those assumptions we can't all hold on to?
Well, the key ones usually discussed are, 1, the predictions of quantum mechanics are correct. Experiments strongly back this up. 2, no faster-than-light signaling is possible. The non-signaling principle, crucial for relativity. 3, realism, specifically local realism, the idea that particles have definite properties before measurement, determined locally, the hidden variable idea. 4, free choice, the idea that experimenters can genuinely choose their measurement settings randomly, uncorrelated with any hidden variables the particles might carry.
Okay, so experiments violate Bell's inequality, meaning they match quantum predictions. That forces us to give up at least one of the others.
Precisely. Since the experiments agree with quantum mechanics, and violating Bell's inequality is a quantum prediction, you have to ditch either local realism, assumption 3, or maybe even free choice, assumption 4, or find some way non-signaling, assumption 2, doesn't apply quite how we think, although most physicists are very reluctant to abandon non-signaling.
So most interpretations lean towards giving up local realism, accepting this non-locality.
That's probably the most common takeaway, yes. Accepting that the world isn't locally real in the way Einstein envisioned. The properties of entangled particles aren't fully determined locally. They're genuinely linked in this non-local way. But different interpretations of quantum mechanics handle this differently. Some might question free choice, others propose different frameworks. It's still debated.
It's fascinating that something so fundamental was, as we said, kind of on the back burner for a while. David Kaiser's book, How the Hippies Saved Physics, apparently talks about how some less mainstream groups kept the interest alive.
Yeah, it's an interesting piece of physics history. While the mainstream focused on applications, some individuals and groups, perhaps less constrained by conventional thinking, kept probing these foundational questions.
And now there's a huge resurgence of interest. Why now?
It's largely driven by practical applications, ironically.
Sure.
Things like quantum computing, quantum cryptography, generating truly random numbers. These technologies rely on the very quantum weirdness, like entanglement and non-locality, that Bell's theorem brought into sharp focus.
So the weirdness turns out to be a resource.
Exactly. Understanding these fundamental correlations isn't just philosophical anymore. It's the key to building entirely new kinds of technology. What was once esoteric is now engineering.
And it's not just some special cases. The source mentioned that almost all entangled states violate Bell's inequality.
That was a later theoretical discovery, yes. It showed that non-locality isn't some rare fluke. It's a general feature of quantum entanglement. It's deeply woven into the fabric of quantum mechanics.
The source also brought up the concept of time in quantum mechanics, suggesting it's maybe not quite the straightforward clock ticking we experience.
It's definitely more subtle than in classical physics. Classically, if you know the present state perfectly, you know the entire past and future, in principle, determinism.
Right.
But in quantum mechanics, measurement itself plays an active role. A measurement doesn't just reveal a pre-existing property. It often yields information that wasn't determined beforehand. It updates our knowledge in a fundamental way.
And this ties into ideas like pre- and post-selection and weak measurements associated with Yakir-Aharonov.
Yes, that's a fascinating area. The idea is, what if you look at a quantum system not just based on its initial state, pre-selection, but also conditional on obtaining a specific outcome in a future measurement, post-selection?
Selecting only the runs of an experiment where a particular future result occurred.
Exactly. And then use very gentle, weak measurements in between. What Aharonov and others found is that the description of the system between the pre- and post-selection can look very strange. Sometimes it's mathematically simpler or more intuitive to describe the intermediate state as being influenced by both the past preparation and the future outcome.
Influenced by the future, does that mean time travel?
No, definitely not information traveling back in time.
Yeah.
That's crucial. It's more like knowing the future boundary condition helps you better understand the probabilities of what happened in between.
The source used a rainbow analogy. Knowing it rained earlier and was sunny later makes a rainbow at noon more likely.
That's a helpful classical analogy for how future information constrains past possibilities. But the quantum case is deeper, because the future outcome itself wasn't necessarily predetermined by the past alone. So post-selection is selecting on something genuinely uncertain. It gives a different, sometimes powerful mathematical perspective.
But it doesn't mess with the overall arrow of time, the fact that entropy increases and things evolve forward.
No, the thermodynamic arrow of time seems robust, likely tied to the initial conditions of the universe, cosmology. Quantum mechanics itself, at the level of fundamental equations, doesn't strongly prefer a time direction, but the universe we observe certainly does.
Okay, one last area briefly touched upon was consciousness and its role, or non-role, in quantum mechanics. There was an old idea about consciousness causing wave function collapse.
Yes, that interpretation dates back to figures like John von Neumann and Eugene Wigner. In the early days of trying to understand measurement, the role of the observer was puzzling. Since conscious observers are the ones who ultimately register results, some speculated that consciousness itself was the special ingredient that caused a quantum system to snap out of superposition into a definite state, the collapse.
But that's not really the prevailing view now.
Not really, no. For one thing, defining consciousness in physical terms is incredibly difficult, if not impossible, currently. Where do you draw the line? A human, a cat, a computer. And there's absolutely no experimental evidence suggesting consciousness has this unique physical power.
So what's the alternative view for why we see definite outcomes instead of superposition?
The leading contender is decoherence. The idea is that any realistic quantum system quickly interacts with its vast environment, air molecules, photons, etc. These interactions effectively entangle the system with the environment in a hugely complex way.
And this entanglement spreads the quantumness out.
Exactly. It rapidly diffuses the coherence needed for superposition across countless environmental degrees of freedom, making it practically impossible to observe the interference effects characteristic of superposition for the system alone. It looks as if a collapse has happened, creating definite outcomes, but without needing a conscious observer to trigger it. Just interaction with a complex environment.
The source mentioned complexity itself, asking if maybe extreme complexity, like in a brain, could lead to new physics. But that's speculative.
Highly speculative. While complexity can certainly lead to emergent phenomena like consciousness itself emerging from neural activity, there's no current physical theory or evidence suggesting that complexity fundamentally changes the known laws of quantum mechanics or plays a direct role in collapse beyond decoherence. It's an open question whether new principles emerge at high complexity, but it's not the standard view.
So wrapping this up, it feels like even with all the success of quantum mechanics, these foundational questions about non-locality, reality, measurement, they're still very much alive. Professor Popescu even suggested we might still be missing some core pillars.
That's a fascinating perspective from him, yeah. Considering how long it took for the profound implications of non-locality itself to be widely appreciated decades after EPR and even Bell. It's plausible there are other fundamental aspects of quantum mechanics, perhaps related to its dynamics or information content, that we haven't fully grasped yet.
Like maybe the dynamical side of non-locality, the Aharonov-Bohm effect was mentioned, more to explore there.
Definitely. These effects, where particles are influenced by fields, even in regions where the field strength is zero, also hint at non-local connections and are still being explored for both fundamental insights and potential applications. It really emphasizes that quantum reality constantly challenges our ingrained classical ways of thinking. We have to keep updating our intuition.
Okay, so to try and summarize this deep dive into quantum non-locality really underscores how strange, how fundamentally different reality is at the quantum level compared to our everyday world.
Absolutely. Bell's theorem wasn't just a clever mathematical trick. It, and the experiments that followed, fundamentally changed our understanding. They forced us to confront that either reality isn't local, or it isn't real in the classical sense, or maybe both in some way.
We have to give up some very basic assumptions about how the world works.
We do. And while physicists and philosophers still debate the exact meaning, the interpretation of it all, the experimental results themselves are undeniable. Nature does violate Bell's inequalities. Non-local correlations are real.
And these aren't just abstract ideas anymore. They're forming the bedrock for new quantum technologies.
Precisely. Quantum computing, secure communication. They're harnessing this weirdness.
So we'll leave our listeners with a final thought to chew on. If reality at its most fundamental level is probabilistic, not deterministic, and involves these strange non-local connections, How might that ripple upwards? Could it change how we think about cause and effect, or determinism versus free will, even in our larger scale world? Does the quantum weirdness offer maybe unexpected ways to look at other complex systems?
That's a deep question. Does quantum uncertainty percolate up, or does it effectively average out? Thinking about those connections is part of the ongoing journey.
Definitely something to ponder. We'd love to hear your thoughts and questions in the comments. Maybe your ideas will spark another deep dive. Thanks for joining us today.